So once again, a very good morning to everyone. Welcome to this talk on under the HPC-AI talk series that the IIT Goa HPC Nodal Center is organizing. And today we have India. We also have attendees from different organizations that includes IIT Goa, some other IITs, C-DAC, and I see some other guests as well. Introduce the two speakers for the day. So let me also share the flyer because so that it gets recorded as well. So we have today with us Mr. Bharat Kaul. He is the director for Parallel Computing Lab, Intel Labs in India. So he has spent almost 2 decades at Intel and has held several leadership positions within product development groups and has been leading the research lab for more than a decade. As part of Intel Labs, Bharat's research focuses on application-driven architectural performance leadership for Intel for multi-core, many-core architectures with special focus on artificial intelligence and high-performance computing. Under his leadership, the lab has had significant contributions to Intel's product roadmap, both in high-performance computing and large-scale AI, 50 plus papers in Tier 1 computing conferences, and also contributions to India's national AI strategy. The lab works in close collaboration with leading academic and industry partners across the globe with significant engagement with the government. So there is also a link in this flyer that has been shared with you all, which is the website or web page for the lab. And you can go through that. It has a lot of interesting information about the work that the lab is doing. The second speaker for the day is Dhiraj Kalamkar. He is a research scientist with Parallel Computing Lab in Bangalore. His research interests include parallel computer architecture, GPU architectures, hardware-specific single node and distributed performance scaling optimizations. Recently, he is also working on analyzing and optimizing deep learning workloads, frameworks, and libraries for Intel Xeon and GPU architectures. Dhiraj has led the early efforts to demonstrate superiority of bfloat 16 over INT16 for training DL workloads, helping set directions for low-precision Xeon roadmap for future generations. He has co-authored over 15 peer-reviewed publications and holds 4 patents. He joined Intel in 2006 as a recent college graduate, and before that he completed his Bachelor of in Maharashtra and earned an MTech. So welcome Dhiraj and Bharat to this session, and thanks a lot for accepting my invitation. I would now request to take over the session first. So Bharat will talk about Intel Parallel Computing Labs activities in India and worldwide. And then after that, we'll have Dhiraj's more technical talk. So over to you, Bharat.
Thank you, Sharad. And let me switch on my video for a minute so that everybody in the COVID times at least sees the face and puts the face to the name. And with my latest COVID haircut, right? All right. Let me switch off the video and so that we use the bandwidth for PowerPoint. Are you guys able to see my laptop? See my screen?
Not yet.
Okay. Technology. How about now?
Yes, we can see it now.
Okay, so Sharad wanted me to give a brief overview of the lab, and then thereafter Dhiraj would sort of take one specific example of our our recent work that we've submitted to Supercomputing 20. Let me quickly go through my slides. I hope to take about 10-15 minutes, and then you get to the juicier part, which is the deep dive into technical work. So we've been in India for about 10 plus years as a parallel computing lab, and as the name says, we're driven by the philosophy that grand challenges of the world all require parallel computing at scale. That's how they become tractable. So therefore, parallel really matters. And that by definition essentially sort of makes our lab focused on high end of the compute. Wherever there is massive appetite for compute, we are always interested in that. And of course, being an industrial research lab, our focus is a lot more. Also, I mean, we are sort of trying to do a balancing act between where we think computing is going to go versus what Intel's business needs are, because somebody has to pay the check for labs as well. So we started out as an HPC lab, and Dhiraj has done a lot of work in quantum chromodynamics with Jefferson Labs in the past, for example. We've done a lot of work in CFD simulations. But 4 or 5 years ago, we sort of saw AI as the new HPC. In fact, actually about 6 years ago, maybe. In fact, the first paper on deep learning as an HPC problem in the industry was from our lab. It talks about distributed deep learning training, and in those days, about 5 or 6 years ago, we had scaled it to a few hundred nodes when nobody would talk about scaling deep learning training beyond a couple of GPUs, right? So last 5-6 years, our focus has been on AI. But there is another big bet that we have in our lab, which is around life sciences, which is around all kinds of genomics and proteomics and all of those things. That's something that, again, we see something that's probably going to become very big, hopefully through this decade, and have been sort of slowly investing on this. Now, our goal is to be an industry role model in application-driven architecture research. And of course, we, as I said, we are an application-driven architecture research lab. So ultimately, we are interested in making sure that Intel's architectures, and when I say Intel's architectures, we mean the broadest, in the broadest possible sense. Our interests span CPUs, GPUs, FPGAs, accelerators. All of those are within the scope. And for all of them, what do we really need to do? We often start with applications that we think are promising or going to be promising or that will drive business forward. And in context of those applications, we sort of have this as a research span, right? I mean, we worry about parallel algorithms. How do we make sure that for these data parallel applications, every single ounce of performance is extracted? We then therefore are able to reason about architectural bottlenecks. Once we are past the performance, we get to reason about architectural challenges, how to speed it up, and therefore sort of focus on how to make processor architecture better, system architecture better, at a large scale level. So therefore, the interests are on the feed side as well. Memory subsystems, networking, power efficiency, accelerators. These are all papers or areas in which we have work or have published papers. And oftentimes, since Intel is not a life sciences company, for example, or a CFD company, we oftentimes end up working with leading academic collaborators across the world, including some folks in India, or with industry co-travelers, as may be the case, in pushing computing boundaries forward. We have a rich history of accomplishments. Most recently, Intel sort of announced AMX, advanced matrix extensions to CPUs. We have deep contributions to that. Dhiraj was the lead author on, the paper on bfloat 16, which is a half precision data type for deep learning, and we were the first lab to show that, bfloat 16 is a good data type for deep learning training. Prior to that, the only mention of bfloat 16 was in context of inference on Google TPUs, right? Although we retained the name bfloat 16 as a credit to Google because they originally had come up with this data type, but had shown it to work for inference. And we have a paper out there that sort of shows how it works equally well for training, and was pretty much adopted then across all Intel product lines. Some of it, Cooper Lake, for example, was just announced, is becoming available later this year, is the first CPU with bfloat 16 as the support. So that is a big deal, getting a $70 billion+ company to adopt something into its main product lines, right? Similarly, Intel's deep learning libraries, whether they are on the compute side or on the communication side, large scale scaling, have roots in our labs. Intel 1 DNN, Intel 1 CCL, they were all created in our labs here in India. Intel had a machine learning product called Knight's Mill that we didn't pursue that product line as a roadmap, and instead we replaced it with GPUs. But again, that was something that came from our labs here. And going really far back, Intel Xeon Phi was again realization of our research going back almost 12 years ago, and the product line was launched in 2012. We've had significant research impact, 50+ papers. We recently had a best paper award at HPC-AI. We have significant contributions on deep learning that I'll talk about maybe a little later. We just recently released a bioinformatics workload that is used by 70K+ users across the world. We have contributions to MPI standards. MPI Forum adopted MPI endpoints a couple of years ago. It was again a proposal that we had worked together with Oxford. We've had industry honors in HPC, for example. We've been in top one, in number one in top 500, number one in Green 500 in the past, and several Intel Achievement Awards, right? And all of this is about significant work done out of here. We lead pretty much the work that we I mentioned here out of India. And this is sort of really how we sort of look at whatever I described, application-driven architecture research. Often in the application domain, we sort of work with domain experts, worry about algorithms, and then from there it goes down to middleware, frameworks and libraries, and then finally hardware. And so it's a strong co-design methodology, if you will, and iterative, where we iterate between architecture and algorithms and sort of improve both of them in the process, and then of course make it available to the rest of the world. So let me talk a little bit about AI, because that's been sort of where majority of our focus has been over the last 4 or 5 years, and sort of walk you through some of the interesting work that we've done. And here's the reason, here the other way to look at it is we sort of divided focus on AI in these buckets and say, hey, look, these are the kinds of things we need to worry about to make sure that AI becomes widely moves much faster than it otherwise would in terms of performance. So first was, for example, scaling needs of AI, right? How do we make scaling faster? Like I mentioned, I think the first paper on this was from our lab. It's out there. I have not referred it in here, but distributed deep learning training. You can see it online. But this was more of a theoretical work. As you would know, a few years ago, when large batches were still not the norm, and ours was the first paper in the industry that to show why do large batches not work, and how large batches end up in getting stuck in very sharp minimas, whereas you need them to sort of go to a more flat minima for better generalization. So as a result, earlier, with large batches, the testing used to be testing error used to be low, but validation errors used to be really bad. So we had first paper with Professor Jorge Nodal, who's the optimization guru, on how to make large batches work. We had proposed a warm start technique that sort of gets over this problem of use of large mini batches, which subsequently Facebook published a subsequent paper taking that technique and creating tuning the hyperparameter, learning rate hyperparameter. But ours was the first paper in that space, how to make large batches work. And first evidence of deep learning as applied to HPC at scale was again from our lab. This was an SC17, I think, paper on deep learning at 15 petaflops. We had worked with NERSC and Stanford University and University of Montreal, looked at LHC data set, looked at climate data set, and sort of had taken it to about 10,000, almost 9,000 plus Xeon Phi nodes. And tackled some of the problems there in terms of science problems. And then all of us remember TPU. TPU as a customized architecture for training, but TPU for the longest time, or the first paper that came on TPU was actually on an inference paper. But was there a TPU for training? And again, that was the first paper from us. In fact, side by side with TPU, TPU folks were presenting TPU architecture for inference. And we had the first ISCA 2017 paper called Scale Deep, which was a scalable compute architecture for training of deep neural networks. It had its innovations on how we need the heterogeneous architecture, compute heavy tiles, memory heavy tiles, and how they need to be interconnected in a in an intelligent topology. The goal again here was can we get to a kind of a petaflop machine in those days. And in those days, of course, now it is normal. But when we had started this research, people were still talking about few CPUs and few GPUs. So this was the first paper on customized deep learning, customized architecture for deep learning training. The reason I'm giving you these guys, and this is an example, is it's to give you guys a sense of the flavor of how we sort of span applications, algorithms, and architecture. These are all examples of that, right? So this is all to make sort of AI faster, scaling needs of AI. And then if you sort of talk about, arithmetic needs of AI or more efficient model deployment, I talked about, bfloat 16, but we have a number of papers in this space. The first paper on half precision for deep learning was use of integer 16. That was at ICLR 17. Then Dhiraj had a paper, led the paper on bfloat 16, which was again yet another alternative to integer 16, which finally was what we pushed across Intel. And then more recently, we put out a paper a few months ago on how to do training with 8-bit floating point. And then can you do inference below 8 bits, right? What does it take to do inference at a ternary residual network? So again, as far as the arithmetic of needs of AI are concerned, significant work has gone over the last 3-4 years on this aspect. And then sparsity is sort of the next big knob as far as AI performance is concerned, right? As far as compute is concerned, of course, most of AI has become memory bound. So there are issues on the memory subsystem side, which again are part of active research. Hopefully we'll have something published there soon. But from a compute point of view, sparsity is the next big knob where you can see performance jumps, but modern day systolic arrays do terribly with sparsity, especially unstructured sparsity. So because the gems are irregular, it causes underutilization of processing elements, and there are significant latency issues that arise. So this was the paper that we sort of published in HPC-AI this year, which won the best paper award. It's called Sigma. It sort of goes goes and attacks this problem. How do we build a sparse accelerator, right? And better model building, right? I mean, can we build better models? Again, we have a lot of work in this space, but let me sort of talk about more what next rather than going in the past, because this was a flavor of the past. And a few months ago, as part of India's national AI strategy, we had worked quite closely with government agencies, DST, Niti Aayog, and we had mooted that, hey, we got to have something like, large-scale AI applied research centers in the country. And finally, I think through DST, as you know, TIHs have come up. One of them is where Intel is participating with the IIIT Hyderabad. And we're sort of taking on two problems there. One is the Vision Zero challenge. The goal is to sort of, can we bring down the number of road deaths from 600,000 to 0 in this decade in India, right? We lose about 600,000 people. And then second really is, this is, call it an investment thesis, if you will. Biology is going to eat the world. And therefore, we want to focus on population scale AI and genomics as use cases or applications that sort of drive research there. With that as the domain, drive both the science of it and as well as the computing needs of this, right? For road-related stuff, we are the first guys to create something called an India driving data set, which is available online. This was, disclosed at ECCV 2018 as part of a workshop. It is available in there. And again, has, so over the last couple of years, we have built a global community around this data set, working with this data set and using this data set. And like I said, for population scale AI and genomics, the goal is for us to, sort of build this kind of a view, if you will. I built it quickly in interest of time, but we sort of see the vision as we want to bring supercomputing in clinics for every single patient. Primarily because we think genomics is going to go mainstream. So we have to worry about, what do different genomics building blocks look like? How do they come together as a pipeline? What does it mean to interpret those genes? At the end of the day, genomics is just like a book. Somebody has to make sense of that book, pages of that book. So AI for omics, and put all of that together to drive better therapeutics, better biomarker prediction, better therapies, and all of those things. And of course, that all of that supported by large-scale compute infrastructure of tomorrow, right? And that's really what the research focus is going to be. That's one of the things that we, in addition to AI, we are betting big on. With that, I would like to pause, and hopefully this gives a good sense of what we are up to or what we have been up to.
So thanks a lot, Bharat, for this. Would you like to take questions now for your part, or would you prefer it at the end?
So we can take questions.
Okay. So I would request our guests in the audience, if you have any question, you can type in the chat box, and we'll take it forward from there.
We can take a couple of questions now. Then.
So maybe I will ask you one question, Bharat. So based on your experience in this field for a long time, and based on the accomplishments of your lab, where do you think the status of HPC related AI research, or this kind of interdisciplinary research is? What is the status in India, and where do you think we should be interested in looking at if we want to make significant progress as a country in the next, say, five years or so, or 10 years maybe?
So I think India has been, I'll be honest with you, India has been a little bit of a struggle for me as far as HPC is concerned, not so much as far as AI is concerned, because a lot of work in AI has been on the algorithm side. And there is a significant, capacity in the country, it so seems, on the algorithm side for AI. On the HPC side, I think there has obviously been, I mean, although I know, C-DAC has been sort of at the forefront of trying to put together large-scale capacities, but it would really help us if we do, for example, take on, interesting research, like, for example, the direction that's happening in HPC is the intersection of HPC and AI. If you sort of look at how Department of Energy sort of goes after, in US goes after some of these problems, and you look at where they are headed, taking out problems of those kinds is where HPC is headed. We have folks in the country that do work. They just need to come together, and I'm hoping, I think, like Sharad, you and I have talked, that we are able to pull together folks across different disciplines that come together. It would seem to me that those collaborations don't happen as strongly in India as, and I could be wrong about it, but I've generally, my experience with working with DOE labs, for example, Lawrence Berkeley labs or Jefferson labs, have been that the physicists and the computer science folks and mathematics folks, they somehow manage to all come together in support of one big problem. So there is a person that's able to paint a big picture of, here's what we need to get done, here's what are different pieces of it, and here is how every single person will be successful in their own space. So even if you're trying to go to a let's say a kilometer resolution on weather modeling, for example, hey, here's how maybe we need to invent next generation of solvers, because maybe the maybe Newton-Krylov doesn't really scale, and we need to solve some mathematics and go to second order methods. Some of these problems, for example, we're tackling with Stanford as part of our Stanford Unstruct SU2 collaboration, right? There was scaling issues with SU2. So we had to sort of, for multiple years, there was maths going on, new maths on, can we use second order methods and all of those kinds of things, even before it becomes a computing problem, right? I think if we sort of take on big challenge problems, whatever those are, and the science guys know them, and then be able to identify that, look, I cannot move forward without having these 5 folks together in the same room, spanning the algorithm guys, the mathematics guys, the computing guys, To me, if we synergize better, we have all the capability in the country. I just haven't seen it come together as well. And then at a scale where we can actually, claim leadership in these top conferences, right? And it is not necessarily only about having exascale computers. I mean, that's one way to do it, and it's a good way to do it because that's what drives people to do it. But even if we don't build that kind of computing capability, but being able to take meaningfully large-scale problems, right, and go after it is kind of interesting, right? And our goal, in my mind, is you have to, as a lab, for example, we compete with in international conferences. They say, hey, let's go take on this biggest challenges that folks have identified and work with those folks that are pushing boundaries both in the domain and those kinds of things.
Okay. So I think there's a lot of emphasis on based on what you said on identifying these large scale problems and combining our efforts in solving those problems, so that you have a greater impact and also it establishes a leadership and necessary human resource and other capabilities in the country.
Yeah, I mean, I see from our perspective, and again, it's a very narrow perspective. I wouldn't say that's the only perspective in the room. But for Intel to start engaging, or companies like Intel to start engaging in the country, we have to be able to, from science point of view, pushing a boundary. And then if that pushing that boundary requires, compute in a way that has never been put together earlier before, then companies like Intel, AMDs and NVIDIAs of the world get interested. Otherwise, you can do all of that. If you can just simply need it to solve some maths, then you don't need computing. Then that kind of coherent ecosystem doesn't come together. So I'm only talking about the problems where when you take on HPC, and there are many such problems that are in there. Including, for example, somebody's just asking me. I think Professor is asking me about COVID vaccine. And navigating chemical space, right? If you have to navigate a billion molecule space, how to do molecular dynamic simulations and how to prune the search space. There's a lot of work going on in there. We are partnering with CSIR and IIIT on that topic, including some of the other companies. Those kinds of things, I think if we take on in the country again, pruning of chemical space, for example, right? Again, it needs a large-scale infrastructure, needs a very strong understanding of molecular dynamics, needs strong AI capabilities, needs large-scale compute. But somebody, I mean, the vision will get driven that way.
Yeah, I think that's very interesting. So here, Professor G. N. Srinivas Prasad, I think he has this question, and there is an emphasis on reduce the time it takes for a candidate vaccine to be commercially or publicly available. So the trial takes a lot of time, and is there a way to let's say model that trial and make it shorter?
So we, like I said, I think we have some work going on with CSIR labs on COVID-19, on vaccines, and but we are not at a stage where I can, answer the question that he's asking with respect to can we shorten the clinical trial. And I mean, I'm not the right person answering that question, anyways. I do not have a good idea of, what trials typically require certain protocols with respect to establishing, safety, and there are certainly some parts that can be accelerated, in terms of identifying the candidate molecules, in terms of identifying toxicity of those molecules, solubility of those molecules. A bunch of those things can be computationally speeded up, but there is going to be an analog portion that we have to worry about nonetheless, right? Actually testing it. You can certainly prune down the candidates, if you will. And there's again interesting work happening. Like I said, I think that's why I mentioned there's interesting work happening, at least in, for example, Argonne National Labs. I know of where they're combining molecular dynamic simulations with AI, generative AI, in fact, and pruning down those search spaces. But again, the kind of scale they are working on, I am not aware of anything like that in India. I mean, the kind of supercomputers they're using, and how they've stitched together multiple supercomputers together and multiple parallel experiments of scale to be able to do those kinds of things. I personally would like to see a lot more of that happen in this country as well, because we have the ability and we have the potential and we have large scale problems.
Yeah, the whole point is, it's one thing to have a successful phase 3 trial on 30,000 people, and quite another thing to have hundreds of millions of people vaccinated. I mean, you are not going to just jump from 30,000 to even a million without an extensive multi-year study. And what happens to the economy in the middle? I mean, it begins with trivial things like you can't meet anyone, to many deep, very deep things.
Of course.
So I think we are not in, of course, biology, modeling biology is all but impossible. But what do you think there is any work in this type of regard? Because that would be a big time help to the whole world. It's very hard. It's very hard because you do not know what model is correct and
Yes.
what model. There's no way you can model even a full cell, let alone a human being. But
that's true.
I mean, what work has Intel done in this regard?
So far, I'm not aware of any particular work on this particular aspect of speeding up phase 3 trials and all of those kinds of things. I'm not aware of anything.
Because, I mean, for example, to put it very directly, teachers and college teachers and colleges, they can't have students in their hostels, because if by chance, even if they are vaccinated, but the vaccination doesn't work for a small fraction of cases, you had it. And then so without hostels for students, the education system starts crumbling for beyond school. And even school, there's so much back and forth going on how to run schools itself. For adults, it's a little better in that they can be forced to behave in certain ways, but students is very difficult. So, has Intel? What is Intel's participation in this type of effort?
So, like I said, I think at the moment, our effort is one in India locally is with CSIR labs on vaccine candidate molecules.
Okay, which lab? We know some of them. Which lab?
I can connect you offline with those. I think Lucknow folks are engaged there, and I think CCMB Hyderabad.
CCMB. Okay, yeah, we know some of them. We know some of them.
So I can connect you offline. But those are sort of, I think, where we are, and there is some work obviously happening in US on the kinds of things that sort of I mentioned, but nothing on the acceleration of clinical trials. I mean, if somebody could crack acceleration of clinical trials, I think you were going to be a billionaire in no time. There's such a problem in healthcare. I mean, there are two problems in healthcare to be solved, so to speak, right? On the therapeutic side, finding the drug molecules quickly and cheaply, and then acceleration of clinical trials. Yeah. That's where all the money is. Okay, so we'll let Dhiraj.
Yeah, I think that was a nice discussion on these aspects. So in the interest of time, let's move to our next speaker. And then at the end, again, we will have some time left for the questions. So thank you, Bharat. And with this, I would now like to invite Dhiraj for presenting his talk on acceleration of Facebook's DLMR system.
Thank you, Sharad, for giving me opportunity to present the work that we recently did. I will switch to the presentation mode quickly. Can you see my screen?
Yes, Dhiraj.
Okay. So means this is the kind of ongoing work in terms of finding the potential, what we can, means how we can utilize the existing CPU systems for the deep learning training. And we have kind of in past done various workloads already, and this was like a recent work done on the recommendation systems. So in general, we have optimized various workloads and kind of tried to show that CPUs are also very competitive in terms of doing the training, though we need to kind of utilize them efficiently. So I will start with a quick example. So I guess everybody is kind of very familiar with this whenever we go for online shopping. Like we do search for one thing and the system kind of throws multiple options. Okay, are you interested in buying these things? Or people buying one thing have already bought these things. So what exactly is happening, or how do the system come up with these recommendations? Or even in general, miss, recommendation is one part, but if we look into the field, miss, for in miss most of these AI techniques or the that are deployed in the background, we have a phase where means a lots of raw data comes in, and there is a phase where the data management is done, the data is sanitized, put together in a proper form or format, and then feed into the model, which does some kind of either prediction or analysis on it. And typically the incoming data has a very high dimensionality in millions or billions of dimensions, and you employ a kind of a sparse neural network or a sparse model, which kind of reduce the dimensionality of your input into tens of thousands of dimensions, and then you apply a learning function that you want to kind of evaluate for or analyze for. So though miss in this particular talk we are talking about a particular one specific recommendation system or taking a miss kind of optimization example, the techniques and the work is kind of more general and applies to much wider things. Okay, so here is what I would cover. I will give a quick introduction to the DLRM systems. Then we will quickly look at how the today's AI frameworks kind of are designed and how they kind of relate to the CPU systems, why there is a performance gap. Then we'll go back to the DLRM. What are the key building blocks in the DLRM system? What are challenges getting the performance out of those? And then we'll show the key results. So, okay, why recommendation systems, or why we picked recommendation system as a interesting problem to look for? So here is a kind of an example within the like a Facebook, where how their compute capacity is kind of utilized. So they have a language models, computer vision model, and the recommendation models, and the relative utilization of the compute within the Facebook is like, if languages take 1x of compute, the computer vision has 10x compute utilization, and the recommendation systems uses 100x of that. So most of the compute in Facebook is kind of utilized here, and this is not just Facebook, but pretty much all these big companies which kind of deploys cloud or works with large amount of data, they have a similar picture. So okay, what is DLRM? So it stands for Deep Learning Recommendation Model. This is particularly a recommendation model that is released or open source by Facebook last year. Inside Facebook, primarily used for kind of ad click-through rate predictions or ranking. And in the industry, means it is kind of becoming a ResNet. So whoever knows about deep learning probably knows about the ResNet 50 in the ImageNet world, and DLRM is becoming a like ImageNet of recommendation systems. So and recommendation system is not just one per specific just workload. It's a kind of a framework to means used with varying the parameters. So it just gives a model of doing certain type of building a certain type of model, but the characteristics of that can vary significantly based on the parameters that are plugged in. And the primary reason why we looked into this is it has a very good characteristics that stresses both of the all parts of the system. So means the bottom picture kind of shows a quick high level model where we have a inputs coming, means dense input coming in and the sparse inputs coming in. So dense features are typically like either it's an input from some another pre-processing model where it represent like contiguous characteristics, and sparse features are more like IDs, like a product ID or user ID and kind of things. So the dense features are passed through a more say a dense model, and the sparse features are typically processed using a lookup table which convert these sparse features into a vectors for more means giving a more computational efficient information. Finally, these features are kind of means combined together in an interaction layer and feed into a top MLP, which predicts or means either do a prediction or ranking kind of things. The final means function that we want to compute. And typically the MLPs are compute intensive. And embedding lookups are bandwidth intensive, as well as embedding tables can be in billions. I mean, the size of embedding table can be in millions of rows, so takes like huge amount of memory capacity. So thus the MLP part of the model kind of stresses on the compute side of the system, and the embedding part kind of stresses on the capacity as well as bandwidth of the system. And when we go distributed, when we look into the how we do the parallelization it across the nodes, it also stresses both all-to-all communication as well as the all-reduced communication in the system. So essentially, it kind of stress all parts of the system, and as we change the parameters of the model, we can evaluate these different parts as well. Okay, so what are the key characteristics in the DL workloads? So typically, we have two dimensions that we look into. One is what is the arithmetic intensity of the model, and second one is what is the size of the model in terms of how much capacity, memory capacity it kind of requires to store. And the convolutional neural networks, they are very high in arithmetic intensity, but model size are relatively very small, in few I mean hundreds, probably hundreds of MBs. Then we look at the neural machine translations or the language models. They kind of grow a little more in the size, but arithmetic intensity is relatively low compared to the CNNs. And the model size for the language models are kind of growing, and in recent kind of years, those are also grown very significantly, like in billions of parameters. And DLRM start with a very large model itself, and the arithmetic intensity, if you look into the DLRM models, they are very, very low in arithmetic intensity, but the sizes and the model size primarily comes from the huge embedding tables that they deploy for processing the sparse features. Also, the lookup, since these are the embedding tables deploy or do primarily the lookups into the table, the access patterns are random. So that also stress or add more pressure onto the memory subsystem. Okay, so let's quickly look at what are the how the deep learning frameworks are designed today, or the this is common to across almost all the deep learning frameworks that are available or widely deployed, like TensorFlow, PyTorch, MXNet, or any widely used frameworks. So there are two parts to the framework. One is the host device or the host CPU, typically a CPU processor used, which primarily manages the resources on the system, like it does builds the model or do the scheduling of the operations, manages memory and devices. It also does data preprocessing or data management and prefetching of the data from the disks. And also, when we go distributed, this part of the framework does the communication scheduling. And most of these tasks are kind of just sequential tasks, and one or kind of very few threads are kind of required to kind of do this processing, though they require, all of these require a lot of memory and thing, but primarily it is a management task and not very parallelized or massively parallel thing. So the second part of the system typically assume is there is a set of accelerators that are connected to the system, and they are kind of designated with the executing the parallel operations, massively parallel operations. So these devices can be CPU, GPU, FPGA, or any accelerator that we can plug in. So all these frameworks are kind of designed to kind of work with this thing. And so by design, they are very naturally kind of fits to the systems with GPUs. Now let's look at how the modern high-end CPU servers look like. So typically they have multiple sockets connected using a high-speed interconnect, and that interconnect keeps the system coherent. So any CPU on any socket can access any memory anywhere without worrying about the data consistency or coherency. Second, we have lots and lots of cores in the system. So each socket can have like tens of or 20, 30, or even 60 cores per socket. Each core has a wider SIMD unit for data parallel execution, and they have a large private caches, which can hold data and make your accesses faster. And then you have a shared LLC per socket, which kind of has a significant capacity and can help you again with the temporal and spatial localities. Finally, each socket has its own memory connected, and all of these are connected using the current interconnect. So memory from any socket can be used or accessed from any other socket. But since the memory is connected to a particular socket, when it is accessed from a different socket, your latencies and the bandwidth can vary. So it kind of creates a non-uniform memory access domains. And all of these aspects are very key to achieving a good performance on these kind of systems. So just to give an example, if we look at our third generation Xeon scalable processors based system, we have up to like 8 sockets on that. Each socket has 28 cores, 512-bit SIMD, and each socket has a 38 MB of cache. So aggregate, we have like 224 cores, or almost more than 400 threads, upwards of like 80 teraflops of compute, and 300 megabits of aggregate cache. And the whole system kind of gives you almost like a 1 terabyte per second aggregated bandwidth. So this is a massive system for doing a training. Okay, so how the performance on these on the CPU system look like, or what are the challenges with achieving a good performance on the system? So first, we look at how the CPU system maps into the AI frameworks of today. So this is the model of system from the framework point of view. And this is what we see as a system. So framework kind of runs on the CPU. It runs on like one or very few number of threads and then offloads the work to the accelerator. So the host part of the framework maps pretty intuitively into the system. So yeah, we have more threads, fine, but of course means the model doesn't change. We can utilize whatever number of threads we have as a host. But where is the accelerator device here? And to solve it means to utilize this massive compute, essentially accelerator kind of, or the framework kind of switches between the host and the accelerator responsibilities of the system. So it starts with the host responsibility, schedules certain operations, and then switch to the accelerator mode, and the parallel op is kind of executed then on all the cores. Then it again goes back to the kind of single threaded execution mode, does its host part, and again switches to the accelerator part. And this is the main source of kind of inefficiencies in today's framework that kind of leads to poor performance on these CPU systems many a times. And that's the kind of focus on our work, like how do we make these frameworks efficient to work with CPU systems and extract the best possible performance on these systems. So inefficiencies can be kind of caused because of the oversubscription, core oversubscription. For example, in certain part of the like a data prefetching or certain part of the processing, the host kind of spawns a background threads to do those things, and then those threads kind of compete when host is, or the system is used in the accelerator mode. So when we just distribute the compute across all the cores, there is a background thread which is kind of slowing down one particular core, and then the overall compute kind of slows down. Or there is a lag between when host is computing, all the cores remains idle. So there is no overlap that is happening between host and the accelerator part of the devices. Another issue with today's frameworks is CPU device is primarily kind of treated as a validation device or correctness check device. So the kernels are typically written in a more simplified way to understand, and just written in a generic way so that it covers all the cases easily. But that kind of has a tax on performance. So the performance of those primitives may not be very well unless you plug in a very optimized libraries or things. So in the context of DLRM, we kind of look into all these things and say, okay, where does the performance stand today and where can we get to? So we did a quick study of the MLPerf config, which is like becoming a standard benchmarking thing for the deep learning workloads and the systems. And we picked the MLPerf config, which uses terabyte dataset for the convergence study. And if I run it on the today's release version of say PyTorch on one of our high-end systems, it would around take 5 days to fully converge the reference version. When we did our optimizations and plugged it into the both PyTorch as well as modified workload, and also combined it with our bfloor16 low precision training thing, we could do the same training in just 45 minutes on a small cluster of 4 nodes. So this is almost like a 160x speed up that we are achieving in time to train. And this is the primary reason is there is a perception that CPUs are not good for training, but we want to kind of change that yeah, no, if you use the system correctly and plug in the right or do the things right way, CPUs can do much better than what they seem to be doing today. In the certain configurations of DLRM, we see more than 100x speed up just even on a single socket. So the code written in the current existing PyTorch is such naively written that small modifications into code leads to like 50-100x speed up. So with this, let's see what did it take to kind of achieve these speed ups, or how do we kind of go about achieving these kind of doing these optimizations in for any other framework, workloads as well. So let's look at what are the key building blocks in the DLRM system. We have, as we talked, we have a MLP portion, the multi-layer perceptron thing, which is both top MLP and the bottom MLP part of the model. Then we have a embedding lookup tables, which can vary from like few less than 10 tables to more than like 50 tables in the system, and number of tables can vary based on the what you are trying to do, and the sizes of these tables also can be varying. You have like in DLRM particular the MLPerf configuration, we had tables as small as like just 3 rows or as large as like 40 million rows in the table. And then we have an interaction op, which is combining the sparse and dense features and to feed into the top MLP. Let's look at each of these in more detail. So what is MLP, or the multi-layer perceptron? It's a just sequence of fully connected layers interleaved by the activation functions like a ReLU. And this is a kind of key building blocks in many DL workloads like BERT, CNNs, or RNNs. So it is a kind of very kind of common as well as well optimized primitive, I would say. And it maps to a matrix multiplication. Primary compute is matrix multiplication, which is also a very well studied op over the years. So optimized libraries are available, and most of the frameworks actually plug in these libraries for efficient execution of this primitive. We still found that there is another 10-20% performance gain we can achieve on these implementations by managing the cache or the TLBs efficiently. So for example, we use a block layout to avoid the TLB conflicts. We also do employ some kind of scheduling and the memory prefetching to bring the data into our larger caches. And finally, we employ a layer fusion. For example, the activation functions are a simple computation like just compare and set a value. So we can fuse those operations along with the gem operation or the output of matrix multiplication. And that kind of saves extra passes over the data to the memory and gives us some benefits. We continue on the building blocks. So the next one is the embedding bag lookups or the embedding lookups. The embedding bag essentially kind of optimizes, again, kind of does a fuse operation on lookup and then accumulate. So it has a random cache line accesses, but it's little different from a typical, say, SPMV kind of thing where you have a random element accesses. So here we are still accessing the full cache line, but the cache line which we pick is random. So there is a potential we can achieve the full bandwidth, but you need to have there's potential issues from the, say, TLB translations or page misses and those things. And we can have a multiple lookup for each of the batch processing we are processing. We can have multiple lookups in a single table, and those lookups are kind of added together. This operation is relatively kind of new into the frameworks, and so not very well optimized yet, or at least not on the CPUs. That's what we observed. And we will kind of discuss what the issues are in next few files. Before that, we just quickly talk about the interaction of what does it do. So there are kind of two common operations that can be done for doing the interaction. It either just take the sparse and the dense output from the MLP and the embedding lookups and kind of does a concatenation to each other, or there is a self dot product that is employed, which again maps to a gem-like operation or the batch gem operation. So okay, let's get little deeper into the what is embedding bag lookup looks like. So typically there is a in the any DL training workloads, there are two passes: the forward pass, which kind of compute the loss with respect to inputs, and then we have a gradient pass or the backward pass, which compute the gradients so that we can update the model. So this is a computation what it does in the embedding lookup does in the forward pass. It's pretty simple. Here is the pseudocode. to kind of summarizes that. So we have a mini batch, say of size n, and for each of the mini batch, we have a two kind of tables. One is the indices table, which tells which index in the embedding table we need to kind of look up or fetch from, and offsets table tells how many indices maps to a particular mini batch element. And so, for example, for the mini batch of second mini batch, we have a three indices that we look up, 0, 3, and 13, and then we kind of sum them up and kind of put as output row. So operation is pretty simple. How do we the SIMD utilization or the vectorization part is also kind of straightforward. E is the width of the embedding table row, and typically it's in like order of 32, 64, 128, or even like 512 kind of thing. So, but it's a large enough to kind of typically span a cache line. So we have a full cache line access, and SIMD utilization is straightforward. How do we parallelize this? This loop, the mini batch, can be split across the cores or processing elements and can be intuitively parallelized. So what happens in the gradient computation or the backward pass? We get the gradients from the next layer as we traverse backward. We look up the offsets and kind of simply expand these gradients, one corresponding to each row that we had accessed in the embedding table. And typically, because we are not accessing all the rows in the embedding table when it is large, we store these gradients as a sparse gradient. So we have essentially we have a list of indices and then the corresponding gradient rows that we probably would use ultimately for the update part. So again, computation is pretty simple. There is just copy operation, and parallelization of this copy across the cores is also straightforward over the mini batch. Okay, so last part is the weight update, or where we update the model or train the model essentially using the gradients. So we now got the gradients in the previous computation. We have the indices, and the update operation is simply you fetch the weight row, take the gradient row, and kind of apply a learning rate on it and update the weight and write it back. So again, computation wise, it's a simple computation, and we can try to parallelize on the mini batch, but there is a catch here. So you have a potential race condition because you may be accessing different for different mini batch, you might be accessing the same indices multiple times. And when you are accumulating these gradients, if you naively do that update, you may have you may just override the previous update by another update, just as a typical race condition. So what do? We simply use some kind of atomic operation there, and we do this update atomically, get done with it. But now on the CPU system, these are the floating point operations, and there is no native atomic support for the floating point elements or data type. So what do? We emulate using the existing construct. For example, we have a couple of options. We have an atomic exchange where we read the value, update it, and then do atomic exchange with the updated value. Another option is the transactional memory extensions that Intel has recently kind of added to the product line. So that kind of allows us to kind of speculatively do the accumulation, and if there is a conflict, hardware detects it, and you can roll back and do it again. So we kind of tried with the both of these approach, and in certain cases we actually when the particular this index distribution is kind of uniform over the table, these approaches works pretty well. But if the indices are clustered to a certain part of the table, there is a lot of contention that happens, and the cache thrashing causes a significant performance loss. So we come up with another technique we call race pre-update, where since the tables are pretty large, we divide them across the available threads, and they simply say we go over the whole index list and say, okay, this part belongs to TID 0, this part belongs to TID 1, and so on. And if essentially, if the index maps to the particular portion of the table or the own portion of the table, that thread will make the update. Otherwise, it will just skip it. And we saw that even with the contention cases, this approach works much better, particularly in the contention cases. And even when there is uniform distribution, this works reasonably well. Though there is an overhead, means as the number of threads increases, because we are going over the whole list of threads, if the number of indices grows significantly or we go with the larger mini batches, it adds some overhead to that. So this is one of the operations that we saw was very naively implemented, but one, because of the race condition, it was not parallelized at all in the kind of PyTorch. So it was just using one single thread for doing this. And even within the single thread, it was implemented such naively that within a single thread, performance was like from 4-5x off. Okay, so that was the optimizations on the single socket or single process level. Then we go with the distributed, and one of the reasons for doing a distributed running is going across node is definitely we want to do that. But even within a single node, we have these multiple sockets and then different NUMA domains, where if we access memory of other socket from the different socket, we have a performance penalties for that. And to avoid that, we kind of use distributed training across sockets as well. Okay, so what are the options we have for distributed training or parallelization options in the distributed training? So typically there are like 3 ways we can parallelize. First is called data parallelism, where the inputs or the to the model are kind of divided. Typically this is called mini batch, is divided across the available number of, say, nodes or ranks, and weights are replicated across the nodes. So we have a repeated copy of weights, and we get a separate distributed copy of the output. And the forward pass kind of continues with this. In the backward pass, because when we compute the gradients, because weights are replicated, the gradient means we get only partial gradients on each, and we need some kind of communication in the only backward pass. Then there is a model parallelism, where we keep the input or replicate the input or divide the input, but primarily the weights or the model is kind of divided across the processing nodes. And this allows us to kind of reduce the size of model when typically the model is pretty large. This kind of helps reduce the size of model and balance the computation. And there is a other approach where we can do both data parallelism and the model parallelism at the same time, which is called hybrid parallelism. Okay, so what are the general rule of thumb here? What do we use, whether we use data parallelism or model parallelism or hybrid parallelism? How do we decide? So a rule of thumb is when the activations are significantly larger than the weights, or the inputs are larger than the weights, typically we use data parallelism so that we divide the activations and make it balanced. If the weights are significantly higher than the activations, we use model parallelism. And the implication is, because we start in the data parallelism, we start dividing activations, they become smaller and sometimes kind of become smaller than the weights. Similarly, on the model parallelism, because we divide weights starts shrinking and can become smaller than the activation. And if you just use one type of parallelism, it can make the system skewed and again have a lower efficiency. So you deploy a hybrid parallelism to kind of balance both. And if this system is skewed, then the communication time can dominate when you go to large number of, say, nodes. Okay, so how do we do distributed training for DLRM? So Facebook, the original version that they open sourced, has a multi-GPU support, which kind of does not a distributed training, but a parallelize across the multiple, say, GPU devices. And they employ a hybrid parallelism where The MLPs are kind of done in a data parallel manner, whereas embedding tables are kind of done a model parallel. And there the choice was primarily made from the device capacity, because embedding tables are significantly larger. They may not fit all in single GPU. So you kind of assign, say, certain number of or part of the embedding tables on one GPU and another part on another GPU and so on. So we kind of kept the parallelization strategies as similar. Because the MLPs are compute intensive and relatively model sizes are small, the parameters are smaller, we have to employ data parallelism and replicate them across the available compute means nodes. The embeddings are divided across the nodes, and that way means it assesses on the memory capacity requirement. Though the CPU means on a CPU you can have a huge capacity and try to fit the most of them in single socket as well. Finally, the interaction op combines these two. So we have now inputs coming from the data parallel part and inputs coming from the model parallel part. So we convert the model parallel to the data parallel so that we can feed it into the top MLP. So it does the conversion of that, and the corresponding communication is also kind of encapsulated into interaction. And inputs are split in a way, means whichever manner we need to feed it to the model, we split the input that way, because these are kind of read from the disk. We can easily choose what to read from the dataset. Okay, so the interesting part when we go distributed is how we reduce the cost of communication that is involved. And one of the best way to kind of avoid the communication cost is just overlap it with the compute, so that the exposed time for the communication is like minimal. So there are opportunities in this model where we can do the overlap. So the forward pass, we start the compute of embedding tables first, because those are completely kind of independent. We start those, and then once the embedding table computations or means embedding lookups are done, we start conversion of model parallel to the data parallel, which involves all-to-all communication. And means in parallel, we do the bottom MLP computation. So while all-to-all is happening on means in the background, we do the MLP computation, and then before we get into the interaction, we wait for the all-to-all to finish. So there is, depending on the size of number of embedding tables and size of embedding versus the computation in MLP, we may get a complete overlap, we may get a partial overlap, but at least we save certain times in the communication. And then we just do a data parallel top MLP. In the backward pass, we start from the top MLP, and the MLPs, because we are doing data parallel, as we say, they require a all reduced communication in back pass. We do the top MLP backward, initiate the all reduce for those gradients, then perform the interaction op, where it again initiate a all to all for converting data parallel to the model parallel, and then we do in parallel, we do bottom MLP computation, backward computation, initiate the all reduce for those, and wait for now the communication to finish. All to all, do the embedding gradient computation, and finally the all reduce is kind of required at the end, so we just wait for that. So we try to extract all possible overlap opportunities and kind of schedule these operations in a way we get the best overlap. Okay, so that was the kind of optimizations we did for the distributed training. And let's look at how we evaluated our work. So we have a kind of a small cluster in the lab, which has like around 32 nodes. 16 of, each node has like 2 sockets. Xeon with 28 cores, and there these 16 16 nodes from the group of 16 nodes are connected to one leaf switch, and then the two switches are connected using a root switch with the 16 links connecting to the root. And this gives us kind of a glimpse of a like a typical HPC system. All the links means essentially we use the Intel OPA means NICs for the connecting these different nodes. And this one means each socket has as I said, means we have a 28 cores and the 6 DDR channels, giving us up to like 100, close to like 100 GB per second memory bandwidth on each socket. And the peak compute is around 4 teraflops on each socket. Okay, one thing means we use for the distributed training, PyTorch has a backend for MPI, and we use MPI communication for essentially doing the communication. But we observe that the implementation of MPI backend in PyTorch has a kind of issues in terms of like the, as we say, the core over subscription. So it for driving the communication, it kind of spawns an additional background thread, and typically that thread interferes with the compute threads and causes a slowdown. So Intel has come up with this collective communication library, and we basically that kind of enables us efficient overlap of computation and communication. It optimizes for the bandwidth utilization by kind of assigning multiple cores for driving the bandwidth. It also kind of supports like prioritization of various types of communication, and also supports like low precision data types and those things. So we plug this into the PyTorch. So the CCL has a kind of generic architecture where it kind of optimizes on the core primitives, and then it provides different plugins to plug into like a PyTorch or TensorFlow or Harwood or various different frameworks. So we put together the plugin for the PyTorch to kind of plug this in and then optimize the communication part of. Finally, this gives a glimpse of the configurations that we kind of studied. So it covers like a small configuration. Sorry, I don't know what is happening. Something is pressing. Okay. So we kind of evaluated our work based on the 3 different configurations: small, large, and the MLPerf configuration. So small one is the same what Facebook has kind of used to kind of give a preliminary data, performance data on their when they open source the DLRM workload. And it's really small, means in the sense like number of tables or the memory footprint and those things. But it means as per the Facebook, means it kind of representative of real workloads, but a scaled down version of that. So we simply kind of scaled the small problem into large one, which kind of scales every aspect, like the size of table, number of tables, the MLP sizes, all of that we kind of scale to little large, so that the representative parts are kind of similar, but it's has a higher compute and higher capacity and bandwidth requirements. And the MLPerf config is what the benchmarking, the MLPerf benchmarking use. So it uses a real data set and has a varying size of tables and the number of accesses, and have a particular convergence criteria. And if you look at the key characteristics of these, if you like the capacity required, we have a small one requires only just 2 GB. So for example, it can simply easily fit in any GPU card also. Large one has a pretty large memory footprint, 384 GB for just the parameters, whereas MLPerf has 98 GB. So they are kind of in the range. Similarly, the amount of read write that happens on the embedding tables per iteration, it's 800 MB to 100 GB, to like MLPerf has only 200 MB. So MLPerf in certain aspects is similar to the small problem, and certain aspects it's similar to the large problem. So it's in between. And the MLP parameter sizes, again, if you look at the small is like just 10 MB, large is like almost a gigabyte of parameters, whereas MLPerf is again just 9 MB of parameters. And the communication side, the small one has pretty small amount of communication also, volume. Large one has pretty huge amount of communication required, like almost a gigabyte of data need to be transferred over the links, whereas MLPerf is again in between around 200 MB. But if you look at compared to the total embedding size, the communication volume for large is, even if it is the highest compared to the total lookup sizes into embedding, this is much smaller. It's just 1%. Whereas for the MLPerf, it kind of matches the access that we do the embedding. So this kind of changes the ratio of the DRAM bandwidth you have versus the communication bandwidth you have, how that impacts. Okay, I will quickly, I don't know what's time. Okay. So I will only walk you through the key results that we have and then refer to our paper that we have recently published. You can take a look at that for the more details. So this is what it shows, like for the small and the MLPerf problem, which we can fit into the single socket, how the performance kind of looks compared to the reference version. So the small problem, we see reduction in like 110x speed up when we optimize that thing on just single socket. And most of this comes from the embedding update operation. As I said, it was just a scalar operation. So we'll look at the splits. And the MLPerf configuration sees around 8x speed up. And the reason why we see difference is we looked at the split of the operation, how the time is split across these three components. And for the small problem, almost 99% of time was just spent in the embedding operation. And within that, it was primarily the update operation, which was horribly slow. So just small changes in the kernel kind of get us that 4000 became like almost like a 14, like 100, more than 100x speed up is just there. Whereas in the MLPerf config, embedding was significantly larger, but still it wasn't like, it was like only probably 70% of total time. And so when we optimize, it became 190 became like 5.9 with the race free. But by the way, the MLPerf configuration, we observed that the atomic exchange or the RTM based implementation gave us some benefit, but it wasn't ideal, or it significantly slowed down the performance due to the contentions. And so the race free version was performing the best here. And when we look at the optimized time for the small problem, embedding and the MLP are kind of now equally divided, or even the rest of the computation is kind of taking the similar amount of time, 30%. Whereas for MLPerf, embedding is like only like less than 20% now. MLP is the most significant part here, followed by the other compute like interaction and some other data related operations. So okay, we got this speed up, but how do you know whether we are done with it or there are certain further opportunities to the optimizations? So we looked at the profiler and kind of calculated the bandwidth efficiency as well as the compute efficiency that we see. So for the embedding part of the code, we look at the bandwidth, how efficiently we are utilizing the bandwidth. And for the small problem, because there are a large number of accesses to the embedding, we get pretty good bandwidth. Means up to 80% of peak bandwidth we achieve. Whereas the MLPerf, the number of accesses are relatively low, but still we get close to 50%. So there might be still some optimizations that we can use and push the MLPerf performance further for embedding side. The compute side, we are around 50 to 60%, and in between 50 to 60% efficiency for the gems. And given the sizes and those things, we done a standalone thing. We are within like 10% of the standalone benchmark here. So MLPs, there is not significant scope to kind of further push the performance. This is the story about single socket. I quickly just show the results for the multi-socket and leave the analysis of that for the reading from the paper. So we get up to like for the small problem, and we are doing a weak scaling here. So we get up to like 6.5x on 8 ranks. So this is like scaling to the 4 nodes. The large problem also scales pretty well, almost gives us more than 13x speed up when we go to the 16x more is compute. And the MLPerf also gives us almost like a 17x speed up on 26 ranks. The reason is on all the highest scaling is kind of restricted the way we do the parallelization. Means we can't go right with the current kind of scheme of parallelization. Means this is limited by the number of embedding tables we have in the system, and we try to kind of scale to those many sockets as a part of our study. So there are future plans to kind of improve it further, but yeah, this is what we have. And the efficiency point of view, the large problem where is there's significant compute and the relatively communication is kind of small portion of the total time, we can get up to like 84% of efficiency even on 64 socket. Whereas MLPerf, the efficiency is little low because the communication required communication is much it takes higher portion of your total time compared to the other two. Finally, I would kind of show our recent result on using the low precision training. We did this for the MLPerf submission, and we get pretty much this is I am showing 2 results here. We have the previous results were like on the SKX and the Skylake versus the Cascade Lake processor generation, whereas these numbers are on a recently launched Cooper Lake generation of Xeon processors. And we can see that for first part when we employ the low precision, primarily speed up is coming from the MLP because that's where we are increasing the number of flops by doing the low precision compute. We expected to have some benefits on the embedding, but due to the kind of nature of the implementation right now, we really don't see much bandwidth savings on the embeddings so far today. We expect to kind of improve it further in the some near future work, but so far we are not able to kind of reduce the time for embeddings, even though we use a kind of low precision even in embedding. And in terms of overall speed up, if you see from generation to generation, we are about 20% better across. Particularly on the small problem, the MLPerf, we get up to like 40% improvement in the 2 rank case. This is primarily because of the increased communication bandwidth, because increase the bandwidth on the links that connects the different sockets. And low precision gives us around 1.4x to almost 1.8x, depending on the configuration and the number of ranks we are using. Okay, with this, I will kind of conclude our work. So we believe that because of the huge capacity that are required in the recommendation models, because of the embedding sizes, embedding table sizes, CPUs are at a great advantage here to be kind of show the good performance. And we show that if we do the simple optimizations and use right libraries to for the computations, we can get from like 8x to 110x just on a single socket. The scaling efficiency can also be pretty good. We have 84% on 64 sockets, and the time to train can be significantly reduced compared to what we see on the reference versions today. And CPU has the additional advantage that it has a flexibility to kind of pick right balance of the system, like how many we have a different SKUs with different amount of cores in the socket. We have a different platform which has different number of sockets in a system node, single node, or which interconnect and how many links we want to use to do the like up scaling. And so that kind of helps with the communication bandwidth and the embedding access bandwidth that we have. Okay, with this, this is the paper that we have kind of put on the archive. You can take a look into that for more details, or I'm open for the questions.
So thanks, Dhiraj, for sharing your recent work. I found it quite interesting. So from the guests that we have, if you have any questions, please feel free to type in the chat box and we'll take them up.
Hello, I have a question.
Yeah.
Yeah, my question is for both the speakers. Like, there were two terms in the presentation. One was regarding hardware software co-design and another term was profiling. So I wanted to ask if anything regarding dynamic profiling in like a dynamic context is being used for the Intel architectures.
So for the second part, means for the dynamic profiling, I'm not sure what do you mean by dynamic profiling, or
Okay, I mean by dynamic profiling, I means when we are doing a static analysis to see the better hardware software co-design platform, what should go where. So that static is based on some static data set that we are putting. In case when we are doing dynamic profiling, so whatever, in case the system is interacting in real time with inputs from outside, so
right.
not necessarily the things that we consider that they should go for acceleration or something, like the scenario could change in a dynamic context based on whatever inputs the system is getting. And there are some architectures evolving to support dynamic reconfiguration or dynamic partial reconfiguration. So in that case, dynamic profiling is of great use. So I wanted to ask if Intel architectures are taking help of dynamic architectures or dynamic profiling approaches.
So means in that sense, the profiling that I showed or we used for optimization, it's like a dynamic. So we use different configurations to study this, and we actually measure the kind of time. We put the timer or use the profilers that are inbuilt into the framework to measure the time across various operations, and then based on that, we essentially either change the algorithm that we are using or kind of change the how we optimize these things.
Okay, so which are you using any tool for it, or you have inbuilt it in the hardware?
So
is there a paper where I can refer to?
So in what I have shown here, this one particularly uses the inbuilt profiler that PyTorch gives us. So pretty much, I guess all the frameworks have some kind of profiling support, which profiles at the operation level. So that's like a more useful for the users, because the app developers, which are kind of thinking in terms of these key primitives and parts of that. Whereas we can also, we use some kind of, for the next generation hardware and even for the low level study, we have a standalone kernels that are implemented, and we use the low level profiler, for example, VTune, to kind of look into the system characteristics, like how many cache misses or conflict misses are happening versus how much bandwidth is utilized in particular parts and those things. So we employ both of these tools. But
okay, but
when we're running the full workload,
VTune is like kind of intrusive. You'll have to add pragmas and all. It's not that it will do dynamic things in runtime.
I'm not sure. Means you don't need to put pragmas or something. VTune you can simply run in the background and collect the profiling. Only problem with typically the problem with VTune or any of these low-level profilers is if the US means it does a in general profiling, so it will aggregate the characteristics on. So particularly like in DLRM, if I run VTune on full workload, it will mix up the characteristics of the embedding, which are bandwidth heavy, with the characteristics of the MLP, which is like compute heavy, and it won't give us a very clear picture. So typically what we do is, as I said, we extract the parts which are kind of which of interest and run them in a loop when we are doing a low level profiling like VTune profiling. So either we would only run embeddings and then profile it on it, or we would only run MLP and then profile it on it. Whereas the framework profilers, which essentially uses the timers around the ops, gives us a much better view of the profile things, or the application level things.
Okay, so is all these details are mentioned in your paper regarding profiling?
Paper has part of it, miss. It can be miss. The PyTorch itself has documentation on how to do the
Okay.
profiling and those things, and Vitune has its own separate documentation. So we didn't kind of
Okay,
include
but
that much. Yeah.
because my research is more into hardware profiling, so that's why I asked this question.
Okay.
Thank you. I'll look into the literature.
So Clint, perhaps you can ask your question.
Yeah, hi Dhiraj, interesting talk. I have one specific question for your paper.
Mm-hmm.
So the question is, so this embedding lookup table, is it a neural network or it's just a lookup table?
So it's a kind of primitive op in the neural building block of the neural networks. So means like in the any framework you have a library of ops like convolution, gems, and those means different types of layers. So embedding operation is a type of say layer. So it has a parameters and this, so you have a wrappers around the just lookup. So you can do the both like lookup and then the training on that lookups.
Okay, so I'm just trying to understand. So what is the overall objective here for this recommender systems? I mean, and how that objective is helping you to update the because you are doing some kind of gradient updates for the lookup table, right?
Yes.
Yeah.
So essentially, means embedding tables are kind of representing a particular feature. Means each row of the embedding table would be representing some sparse feature. Maybe a product, I mean, describing a product, or maybe describing a or user. And essentially, these embedding tables are used to kind of make it easy to kind of correlate these different things. So for example, if two users have a similar likings, their vectors will looks in similar in some sense. So we want, I mean, they are initialized with the random values at the beginning, and the training essentially makes them look similar, so that when those two users are trying to search something, probably they will have a similar results kind of shown.
Okay. So one continuous, I mean, one more question, I mean, in this line. So the question is that so when, I mean, I'm trying to think about how we can generalize this for other set of algorithms, like how this framework. So this type of framework is useful when there is, I mean, there is more lookups happening in the model, or because this MLP GPU based systems are working well, right? So for a system like this, it will be performing well when you have when I understand that when the model is big, this is useful, and this type of framework is useful when we have lookups happening in the model itself.
No,
something
so
like that.
as I said, in general, means if we means that today we see many a times we see a low performance CPU performance, primarily because things are not either not used properly, means you have over subscription and kind of things, or the operations, the framework writers haven't optimized the operations for CPU. So in general, means in we see like whatever the means gap there is between the flops or bandwidth in terms of like GPU versus CPU, the performance difference is also in the similar order. So efficiency wise, CPUs have a similar efficiencies to that of GPUs. In particularly the DLRM case, we are saying that because the embedding tables are large, you really need a multi GPU system to even start training or doing something because of the capacity itself. Like for example, the MLPerf configuration, the parameters itself are like 100 GB, so you can't fit it in like one GPU and can't train it. But in the CPU, means you can you have an option to kind of go with just a single node and still do the training, or even when the model means we have seen like models have billions of parameters or even trillions of parameters. In that case, you would need a massive GPU system to even do any kind of analysis on that or train on that. Whereas CPU, you can have a small cluster and you can do that. And another point here was, means CPU clusters are kind of widely available, particularly in India. Means we have a means many small CPU clusters, so those can be used for doing quick experiments or doing the DL analysis.
I think
Okay,
that's the point that
Yeah.
I think one of the slides that Dhiraj had, existing CPU architectures that most of us probably have in our labs, they itself can go 100x faster. Right? Just if you do the right things as far as CPU is concerned, right? I mean, I think if Dhiraj can go back to the performance slide, what used to take maybe like a week to train is now 45 minutes.
Yeah.
On the same, if you just did the things right, understood what, HPC community is well versed with architecture specific optimizations. So it's the same problem. If we sort of look at the workload and map it effectively to underlying architecture, the same CPU can give you, 100x or more kind of speed ups. And this kind of a workload, I mean, even though, DLRM, I guess, as Dhiraj pointed out, consumes a lot of compute as far as cloud is concerned. But underneath it, it also represents this whole, sparse to dense, learning infrastructure, if you will. How do you go from something very sparse to dense, and and that sort of is not necessarily just an advertising problem, right?
Yep.
Okay. Thanks. Yeah.
Okay, so I think Dhiraj also answered one of my questions while answering Clint's question. So I don't have. I won't ask any question further. This session has run for quite some time, and I think it went quite well. And with the interaction, I can see that liked this session. So on behalf of the IIT Goa HPC Nodal Center and everybody else here, I would like to thank Dhiraj and Bharat once again for the wonderful session that
Our pleasure.
we can also have sessions in the future. Okay, though we exceeded our time today, but by almost half an hour, I guess. But I hope you guys like the interaction. So with that, I think we can wind up today's session, and we'll meet up again. We'll schedule some other talk from you guys again.
Thank you, Sharad. Thanks, everyone.
In the near future, very soon.
Thank you, Dhiraj.
Thanks, everyone. Take care.
Bye.
Thanks. Bye-bye.